Hello, fellow engineers and industry experts. I'm Abhinav Chunchu. I've been working as a software engineer from past 8 years. At present, I'm working in Lowe's as a senior software engineer. Today, I'm presenting the Quantum Leap, Revolutionizing the Secure Software Development with Quantum Computing. This presentation explores the transformative impact of quantum computing on software development paradigms. It examines the fundamental principles of quantum computing, including superposition and entanglement and their potential to revolutionize the computational capabilities across various industries. This presentation discusses the project growth of quantum computing market, its applications in the fields such as drug discovery, cryptography, and the challenges it presents to traditional software development practices. Today's key areas of focus is on the design of quantum algorithms, the emergence of quantum-specific programming languages, and the development of hybrid quantum classical computer models. The presentation also addresses the significant challenges facing in the quantum computing world, such as error correction, scalability, while highlighting the exciting opportunities it offers in cryptography, drug discovery, financial modeling, machine learning, and climate modeling. Through an analysis of recent experimental achievements, the future projects, this presentation provides a comprehensive overview of the quantum computing landscape and its implications for the future of software engineering. Let's compare the classical computers with the quantum computers. Quantum mathematicians and quantum physicists made clear that the quantum computers are not to replacement of classical computers. Quantum computers are used to solve the different set of problems which cannot be solved by the classical computers. To put in a perspective, quantum computers are not for the internet browsing or streaming a video or browsing in the Google or something. It's just meant to calculate certain problems which the classical computers cannot have capability of. At its core, quantum computing leverages the principles of quantum mechanics, utilizing the quantum bits called qubits instead of classical bits. Unlike classical bits, which can only be in state of 0 or 1, qubits can exist in superposition of states, allowing for simultaneous processing of multiple possibilities. This fundamental difference enables quantum computers to solve certain problems exponentially faster than their classical counterparts. The power of quantum computing lies in its ability to manipulate the quantum states. For example, a 50-qubit quantum computer can represent up to 2 to the power of 50, which is approximately 1.13 into 10 to the power of 15 states simultaneously, a scale far beyond the capabilities of a classical computers. This vast computational space allows the quantum computers to explore the complex problems efficiently. One of the most promising applications of quantum computing is in the field of cryptography. For instance, Shor's algorithm and the quantum algorithm for integer factorization can factor large numbers in polynomial time, potentially breaking many current cryptographic systems. To put this into perspective, factoring a 2048-bit RSA key, which would take approximately 300 trillion years using a classical computers, could theoretically be accomplished by a fault-tolerant quantum computer in just 10 seconds. Similarly, Grover's algorithm, a different quantum algorithm, Grover's algorithm provides a quadratic speedup for an unstructured search problems, with significant implications for database operations and optimization tasks. In a database of 1 million unsorted entries, a classical computer would need to check an average of 500k entries to find a specific item. A Grover's algorithm can find the same item with only 1000 quantum operations, demonstrating the substantial speedup. Let's see the quantum market size and qubit count. The current quantum market size is $15 billion and the estimated qubit is 800 qubits. The leading quantum computer is owned by the IBM IBM Q, also called the IBM quantum computer. And the estimated qubit growth in the year 2030 is 51,200. And the estimated market size of quantum computing is $65 billion. Many countries are fighting to gain the quantum supremacy. Let's go through the quantum principles. There are three major quantum principles which are fundamental in quantum computing: qubits, superposition, entanglement. Qubit is a basic unit of quantum information. Superposition is ability to be in a multiple state simultaneously. Entanglement is a strong correlation between qubits, even over the large distances. Okay, qubits. Let's go a little deeper into the qubits. A qubit, short for a quantum bit, is the fundamental unit of quantum information and quantum analog to the bit in classical computing. Unlike classical bit, which can be either 0 or 1, a qubit can represent a 0 and 1 or any quantum superposition of these states. This property allows quantum computers to process complex computations more efficiently than the classical computer in certain situations. So, superpositioning. Superpositioning is a principle of quantum mechanics where a qubit can exist in multiple states simultaneously. Instead of being in a definitive state of 0 or 1 like in a classical computer bit, a qubit can be in a state that is a combination of both 0 and 1. It's represented as a qubit state. The qubit state is alpha of 0a plus beta of 1, where alpha and beta are the complex numbers that determine the probability of qubit being in the 0 state or the 1 state when measured. Superpositioning enables quantum computers to perform many calculations simultaneously, leading to the potential or massive parallelisms and faster processing speeds for certain type of problems. Let's look into the entanglement. Entanglement is a fundamental phenomena in quantum mechanism where two or more quantum particles become interconnected in such a way that the state of one particle is directly related to the state of others, no matter how far they are. So this means the properties of entanglement particles are correlated even when they are separated by large distances. One of the major key features of entanglement is the instantaneous correlation. When two particles are entangled, measuring a property such as spin, position, or polarization of one particle instantly determines the property of other, regardless of distance between them. This correlation occurs faster than the speed of light. This puzzled the Einstein and led him to refer this as a spooky action at a distance. And the quantum state independence is another key feature where the overall quantum state of an entangled system cannot be described independently of the state of individual components. Instead, the system must be described as a whole with a shared quantum state. Applications in quantum computing or applications in entanglement are quantum computing and cryptography. In quantum computing, entanglement is used to link qubits in such a way that they can perform complex calculations more efficiently. Entangled qubits can exist in a superposition of states, enabling quantum computers to perform multiple solutions to a problem simultaneously. In quantum cryptography, entanglement is used in protocols like a quantum key distribution, also called as QKD, where the security of the communication is guaranteed by the principles of quantum mechanics. I have an example here. If two qubits 1 and 2 are entangled, where 1 is in a red state and then 2 instantaneously will be found in a corresponding state is blue. Depending on the nature of their entanglement, regardless of the distance between them, if 1 is in red, 2 will correspondingly be in the state blue, again instantaneously. Entanglement is one of the most intriguing and non-intuitive aspects of quantum mechanics. This phenomena challenges the classical notions of locality and separability of a classical computer. Let's discuss about the quantum algorithms. There are two major quantum algorithms, a Shor's algorithm and Grover's algorithm. A Shor's algorithm is a quantum algorithm developed by a mathematician Peter Shor in 1994. It efficiently solves the problem of an integer factorization, which means it can find the prime factor of a large composite number. This is particularly important because the security of many encryption systems, such as IRA, is based on the difficulty of factoring large numbers. This algorithm creates a major impact on cryptography. If a large enough quantum computer were built, Shor's algorithm could break widely used cryptographic systems like RSA, threatening the security of current encryption methods. Grover's algorithm. Grover's algorithm was developed by Love Grover in 1996. This is a quantum algorithm that provides the quadratic speedup for an unstructured and unsorted search problems. Some of the key points of a Grover's algorithm are the searches are unsorted database or solves the problems that can be reduced to an unstructured search. Example, finding a pre-image of a hash function. And the Grover's algorithm's efficiency, it provides a quadratic speedup which is significant but less dramatic than the exponential speedups offered by the Shor's algorithm. The Grover's algorithm applications are, it can be used to speed up a wide range of search problems, making it relevant for the cryptographic attacks like a brute force key searching. However, it does not completely break the cryptographic systems, it just reduces the effective security level. Let's discuss on the shift in software development to the quantum computing world. So, algorithm designs. Developers must now consider the quantum algorithms that exploit the superposition and entanglement. For example, the quantum approximate and optimization algorithm, which is called QAOA, has shown promising results for combinative optimization problems, outperforming classical algorithms in certain scenarios. In recent study, QAOA has applied to the max cut problem on graphs with up to 23 nodes, achieving a performance ratio of 0.9616 compared to the best known classical computers classical approximation algorithm ratio of 0.8785. This demonstrates the potential of a quantum algorithm to solve the complex optimization problems more efficiently than their classical counterparts. Programming languages. The evolution of quantum programming languages includes new quantum-specific languages and frameworks have emerged, such as Qiskit, called Q-Sharp, and Cirq. These tools abstract the quantum operations, allowing developers to write the quantum programs without deep expertise in quantum physics. For instance, Qiskit has been used to implement the quantum support vector machine that achieved 100% accuracy on a small dataset, demonstrating the potential quantum machine learning. In other applications, researchers used Q-Sharp to implement a quantum algorithm for solving a linear system of equations, achieving a quadratic speedup over classical methods of certain problem instances. The next shift to in software development is hybrid computing. The integration of quantum and classical systems is becoming increasingly important. Google recently demonstrated a quantum supremacy used in a hybrid approach where a classical computer managed the overall workflow on the quantum processor performed in a special dataset. This hybrid model is particularly relevant for near-term quantum devices known as an noisy intermediate scale quantum, which is also called as NISQ. So these computers, for example, in recent experiment, a hybrid quantum classical algorithm was used to simulate a chemical reaction mechanism involving up to 20 qubits of a quantum part and classical optimization techniques. This hybrid approach achieved the higher accuracy than purely classical methods, which requires fewer quantum resources than a full quantum simulation. The shift towards the quantum computing also impact the software testing and verification. Traditional testing methodologies or traditional testing approaches are insufficient for the quantum systems due to the probabilistic nature of a quantum measurements and the exponential growth of a state space with the number of qubits. The new verification techniques such as quantum tomography or randomized benchmarking are being developed to assess the reliability and performance of a quantum computer. So this is some performance metrics compared with the quantum computer and classical computer. You could clearly see in the year 2020 the performance of quantum computer is not so high compared to a classical computer with the 50 qubits, but with the increase in the performance has increased exponentially in the current 800 qubit quantum computer which is owned by IBM. The performance difference between classical computer and the quantum computer for certain complex calculations and problems is more than double, actually more than triple. And the year 2025, the scientists and the mathematicians are planning to increase the qubit to 1000, where the performance improvement of a classical computer and the quantum computer will be no match. Let's see the challenges in the quantum software engineering. So as there is a shift in software development towards the quantum computing, it has certain challenges. One of the main challenges are error correction. So before going to error correction, there is a debugging complexity. In instance, in a classical computer, it's very easy to debug a problem. It's very easy to debug a API or anything because it have only one state for a bit. So this makes it easy for us to debug. But the debugging in quantum state is very, very difficult and almost near to impossible. So the quantum state collapses upon measurement. And the next issue is error susceptibility or error correction. Quantum systems are highly susceptible to errors due to the decoherence and noise. The current quantum error correction codes require a large number of physical qubits to create a single logical qubit. For example, the surface code, a promising quantum error correction scheme, requires approximately 1000 physical qubits for one logical qubit. The recent experiments have demonstrated the error correction on a small scale with a 7 qubit system achieving a logical error rate of 3.2% compared to the physical qubit error rate of 4.8%, showcasing the potential improvement through an error correction. Scalability. The current quantum processors have a limited qubit counts. IBM's latest quantum processor, Eagle, boasts around 127 qubits, but millions of qubits may be needed for a practical and large-scale quantum computing. This challenge lies in maintaining the quantum coherence as the system scales up. For instance, the current superconducting qubit systems have a coherence time on the order of 100 microseconds, which limits the number of operations that can be performed before the error accumulate. Algorithm development. Designing an efficient quantum algorithms for the real-world problems remains a significant challenge. While quantum algorithms show the theoretical speedups, the translating those into a practical advantages require a careful consideration of problem structure and quantum resource limitations. For example, Shor's algorithm for factoring a large number requires on the order of 20 million qubits to break a 2048 bit RSA key, far beyond the current capabilities. As there is challenges, despite these challenges, the quantum computing opens up exciting opportunities across the various domains. Cryptography. The post-quantum cryptography is an active area of research, with NIST currently evaluating the candidate algorithms for standardization. For instance, the crystal's KBR key encapsulation mechanism and the crystal's dilithium digital significant have been selected as a primary algorithms for the post-quantum cryptography standardization, demonstrating progress in this field. Drug discovery. The quantum computers in the current world play a major role in the drug discovery. The quantum simulations could dramatically accelerate the drug discovery process. The recent simulations of small molecules have demonstrated the potential of a quantum computers in this field. For example, researchers have successfully simulated the ground state energy of a water molecule using a 12-qubit quantum processor, achieving a chemical accuracy. This paves the way for the more complex molecular simulations that could revolutionize the drug design and the material science. Financial modeling. The quantum algorithms for the portfolio optimization and risk analysis are being developed, with potential to outperform the classical methods for the complex financial models. In recent study, a quantum approximate optimization algorithm (QAOA) was applied to a portfolio optimization problems, demonstrating a potential quadratic speedup over a classical methods for certain problem instances. Machine learning. The quantum machine learning algorithm shows promise in enhancing the pattern recognition and data analysis. For instance, a quantum support vector machine has demonstrated the ability to classify the data with fewer computational resources than its classical counterpart, potentially leading for more efficient AI systems. Climate modeling. The quantum computing could significantly improve the climate models by enabling more accurate simulations of complex atmospheric and oceanic processes. The recent research suggests that the quantum algorithms could provide the exponential speedups for certain fluid dynamic simulations, which are crucial for the climate prediction. This is the projected quantum computing performance improvement. In the year 2024, in the current, the error correction efficiency is 40 and the drug discovery accuracy is 94. So the error correction efficiency has been increasing gradually, and the year 2028 it is predicted that error correction efficiency will be on par or at least near to the drug discovery accuracy. This chart clearly shows the improvement of error correction in the quantum computers. I'm going to conclude with some of the few key points. The advent of quantum computing represents a paradigm shift in the computational technology with far-reaching implications for software development and numerous scientific and industrial applications. As we have explored the unique properties of quantum systems, offer the unprecedented and computational power, and enabling the solving complex problems intractable for classical computers. However, harnessing this power requires a fundamentally reimagined software development practices. For algorithm design to programming and testing these methodologies, we need a quantum computer that's powerful enough to have these algorithms to run. While significant challenges remain, particularly in the areas of error correction, scalability, algorithm development, and the potential benefits of quantum computing are immense. From breaking current cryptographic systems to revolutionizing the drug discovery, optimizing the financial portfolios, enhancing the machine learning capabilities, and improving the climate models, the quantum computing promises to transform the multiple sectors of science and industry. As per quantum hardware continues to advance, with qubit counts and coherence time steadily improving, the software development community must evolve rapidly to keep pace. This evolution will require interdisciplinary collaboration and development of new skills, tools, and methodologies. The coming years will be crucial in translating the theoretical potential quantum computing into practical real-world applications. In conclusion, while we are still in the early stage of quantum computing era, it is clear that the technology will play a pivotal role in shaping the future of computation and the software development. As researchers and developers are continue to push the boundaries of what the possibility with quantum systems, we can anticipate a new wave of innovations that will redirect our approach to solving some of the world's most complex problems. Most of the quantum scientists and physicists assume that in the quantum era we are still in a transistor state. To evolve from transistor state to the current computer state, it might take a lot of time. But the quantum computers are growing significantly larger and larger, and the qubits are increasing. There is a huge opportunity for the software development in the quantum world. So these are some of the references I used for the diagrams and the metrics.